The story of a great thinker often begins long before the world takes notice of him. It begins in the quiet places, in the days of youth, where curiosity is not yet shaped into theory, but burns as a restless hunger to understand the unknown. The man who would later shape the destiny of modern physics was born in the year 1901, a year standing on the edge between the old world of certainty and the new world of doubt. Europe at that time was alive with invention, industry, and cultural change. The 19th century had been an age of progress, filled with the confident belief that science could explain everything if given enough time. Yet in the heart of this young child's life, the foundations of that certainty were already beginning to tremble. He was born into an educated family, where music, literature, and scholarship surrounded him. His father was a cultivated man, deeply interested in philosophy and the arts, while his mother was a figure of warmth and guidance. From his earliest years, the child was surrounded not only by love, but by the expectation that knowledge was a path worth pursuing. Unlike many children of his time, his early environment gave him both encouragement and the freedom to explore his mind. This was not a household where curiosity was stifled. It was one where asking questions was seen as a sign of intelligence and promise. As he grew, his love for mathematics began to show itself. Numbers and patterns seemed to speak to him in ways that went beyond mere school exercises. Where other children saw arithmetic as a chore, he saw it as a puzzle, a game that revealed hidden rules of the universe. It was in the structure of equations that he found a sense of harmony, as though mathematics was a secret music that only those who truly listened could hear. Even before he reached adolescence, he was seen by his teachers as someone unusually gifted, someone who looked at problems with a sharpness that few others possessed. School life in those years was strict, shaped by the traditions of German education. Discipline was valued, and rote learning was often seen as the path to knowledge. But for him, discipline was not a burden, because it was matched with passion. He studied Latin, Greek, and history, but it was in the sciences where he excelled most. Physics drew him like a magnet. The experiments, the demonstrations, the mysteries of light and motion fascinated him. When he looked at the world, he did not simply see objects moving or forces acting. He saw questions waiting to be asked, and he wanted to be the one who found the answers. By his teenage years, his name was already whispered with admiration among his teachers. They saw in him not only intelligence, but a rare clarity of thought. He was not content to memorize formulas. He wanted to understand why they worked, to pull apart the hidden gears behind nature's machine. This was not the kind of student who accepted explanations at face value. When told of Newton's laws or Maxwell's equations, he would probe them, test them, and imagine where their limits might be. That hunger to find the limits of knowledge would one day define his career, but even in youth, the seed was already there. Outside the classroom, he developed another side of his mind. He was not a boy lost only in numbers. He was deeply interested in philosophy, in music, in the great questions of meaning. His father had been influenced by the traditions of German philosophy, and the young student absorbed those ideas with eagerness. The writings of Goethe, the ideas of Kant, the reflections of the poets and philosophers of Europe became part of his inner world. He was not a narrow specialist, but a thinker who saw science and philosophy as two branches of the same tree. This balance between the technical and the reflective would later give his theories a depth that reached far beyond laboratory walls. At home, evenings were often spent in long conversations, reading aloud, or playing music. The household was filled with intellectual energy, yet it was never cold. This combination of warmth and intellectual challenge created in him both confidence and humility. He grew into a young man who believed not only in the power of knowledge, but in the importance of questions that could never be fully answered. The dawn of the 20th century was a time of extraordinary change in science. While he was still in school, Albert Einstein was publishing papers that challenged Newtonian certainty. Max Planck had introduced the idea of energy quanta, a radical notion that energy was not continuous but came in discrete packets. These ideas were stirring in the scientific world, while the young student was still mastering the basics of calculus and mechanics. Though he could not yet grasp their full meaning, he sensed that science was entering a new age. It was an age where certainty was slipping away, and new theories were needed to make sense of nature's mysteries. When the time came for him to enter university, there was little doubt about the path he would take. He chose physics not as a career, but as a calling. In the halls of higher learning, he found himself surrounded by other bright minds, but even among them, he stood out. His professors noticed his ability to think independently, to see connections others overlooked. He was not merely repeating lessons, he was quietly beginning to question the boundaries of knowledge itself. The early 1920s were years of great debate in physics. Old models of the atom were failing, and new mathematical frameworks were being tested. For him, this was not chaos but opportunity. It was precisely the kind of environment where a questioning mind could thrive. The young man's style of work was distinctive. While others rushed to publish or to follow established trends, he worked with patience and depth. He often preferred to think slowly, to let an idea mature in his mind until it revealed its hidden shape. He would walk for hours, reflecting on equations in his head, allowing the rhythm of thought to lead him to insights. His classmates sometimes misunderstood his silence, mistaking it for hesitation. In truth, it was the silence of someone who was listening to the deeper voices of logic and intuition. In these years, he developed the intellectual tools that would later allow him to build his most famous theory. He mastered advanced mathematics, studied the physics of atoms, and absorbed the revolutionary ideas that were emerging. But more than knowledge, he developed courage. The courage to imagine that the accepted answers might be incomplete. The courage to say that the universe might not be fully knowable in the way classical science had promised. The young physicist was also deeply shaped by the times in which he lived. Europe was still recovering from the devastation of the First World War. His country, in particular, was marked by political turmoil, economic crisis, and uncertainty about the future. For many, these were years of despair, but for him they were also years of determination. If the outside world was unstable, then the inner world of science offered a place of order and meaning. His studies became a refuge, a way to rise above the struggles of daily life and to focus on something eternal, the laws of nature themselves. In those days, universities were alive with debate. Students and professors argued not only about physics, but about philosophy, politics, and the role of science in society. He was never a loud voice in these discussions, but his quiet contributions carried weight. He believed that science was not separate from life, but deeply connected to the fate of humanity. He studied not only with his mind, but with his conscience. By the time he completed his formal education, he had already earned a reputation as one of the most brilliant young physicists of his generation. His doctoral work displayed not just technical mastery, but originality of thought. Professors who had trained many students recognized in him something different, something rare. They could see that he was not simply adding to the knowledge of physics, he was preparing to transform it. This first chapter of his life, from childhood through education, reveals the foundations of the thinker he would become. The boy who found joy in numbers became the young man who saw equations as windows into reality. The teenager who devoured philosophy grew into the physicist who asked questions no one else dared to ask. The student shaped by a turbulent age became the scientist who would redefine certainty itself. And all of this was only the beginning. The journey of this young physicist, already marked by brilliance and determination, did not stop with the completion of his education. What had been planted in his youth now began to grow into something that would influence the very foundations of modern science. His early years were more than a prelude. They were the crucible where his character and method of thought were forged. To understand the greatness he later achieved, one must see how the seeds of his upbringing, education, and youthful curiosity flowered into the principles that shook the world. The man who would one day teach humanity about uncertainty had himself been formed in a world of searching, questioning, and longing for meaning. Even after leaving behind the structured walls of school, he carried within him the discipline of rigorous learning, combined with the restless energy of a seeker who refused to stop at the first answer. For him, the end of formal education was not a conclusion, but the opening of a larger classroom, the laboratory of the universe itself. He entered this stage of life with a sharp awareness that the mysteries of existence were vast, and that science was only beginning to scratch their surface. It is important to imagine him in these years, walking through the courtyards of universities, sitting quietly in libraries, gazing at chalkboards covered with symbols, and engaging in long conversations with fellow students. Each moment was another step toward the creation of a new way of seeing reality. He was not isolated in his brilliance. He learned from his teachers, debated with his colleagues, and absorbed the spirit of discovery that defined the early 20th century. The intellectual community around him was in upheaval. Old certainties were being dismantled by fresh ideas, and he was among those who welcomed this disruption not with fear, but with fascination. The early part of his career saw him traveling to different centers of learning, meeting with some of the greatest minds of the time. He crossed paths with figures who themselves would become legends, scientists like Niels Bohr, Werner Heisenberg, and Max Born. The young physicist was deeply influenced by these interactions, but he also gave something back. His way of thinking, shaped by years of disciplined questioning, allowed him to contribute insights that impressed even the senior scholars. These exchanges were more than academic discussions. They were the sparks that ignited a revolution in physics. Yet for all the brilliance of these circles, he never lost the grounding given to him in childhood. He still carried within him the influence of philosophy, literature, and art. While others focused solely on equations, he retained the broader vision of a thinker who believed that science and human meaning were inseparable. This gave him a depth of perspective that few others possessed. He was not content merely to describe the world with mathematics. He wanted to understand what those descriptions meant for the way humans saw reality itself. This fusion of technical skill and philosophical depth made him a unique figure in the scientific landscape of his time. Even in these productive years, he often worked in solitude. He had a habit of withdrawing, of seeking quiet places where he could think without interruption. He would wander through forests or sit alone in a study, letting problems turn over in his mind for hours, even days. To those around him it sometimes seemed mysterious, as though he disappeared into silence. But when he emerged, it was often with an idea that would change the course of research. His way of thinking was like the slow growth of a tree, invisible on the surface but powerful in its roots. The Europe of his youth was still unstable. Political unrest, economic hardship, and the lingering wounds of war shaped the atmosphere. For many young people, these were years of confusion and despair. But for him, they were years of resilience. He threw himself into the pursuit of knowledge with even greater intensity, perhaps as a way of finding order in a world of disorder. The stability of mathematics, the clarity of physics, and the enduring power of intellectual discovery gave him a sense of purpose when the world around him seemed uncertain. There is something profoundly human in this stage of his life. He was not only a scientist, but a young man navigating questions of identity, purpose, and responsibility. He read widely, thought deeply, and began to form his own views not only about science, but about life itself. This personal growth was inseparable from his intellectual growth. The young physicist was becoming not just a master of equations, but a philosopher of existence, a man who saw science as a dialogue between humanity and the cosmos. The friendships he formed during these years were also important. Among his colleagues, he found kindred spirits, people who shared his passion for discovery, his willingness to challenge assumptions, and his drive to explore the unknown. Yet even among them he stood apart not in arrogance but in vision. He often saw further than others, not because he was smarter, but because he allowed himself to think differently. He was willing to imagine that the foundations of science themselves might need to be rebuilt. This courage of imagination set him on the path toward his later discoveries. As his reputation grew, he began to attract attention from prominent scientists. Invitations came for him to lecture, to collaborate, to contribute to the growing body of research. With each paper, each lecture, his voice grew stronger in the chorus of physicists who were redefining the nature of reality. But what is remarkable is that even as his professional life blossomed, he remained deeply humble. He never sought fame or recognition for its own sake. His loyalty was to the truth, to the pursuit of understanding, to the quest that had begun in his childhood and never left him. In this sense, the first keynote of his life, the shaping influence of early education and curiosity, was not only a phase but a constant presence. It was the foundation upon which everything else rested. The boy who once marveled at mathematics was now a man who wielded it with power. The teenager who questioned formulas was now questioning the very laws of physics. The student who absorbed philosophy was now creating theories that would influence philosophers for generations. Every part of his upbringing, every lesson, every moment of curiosity had prepared him for this role. It is easy to think of genius as something that appears suddenly, like lightning striking from the sky. But in truth, genius is often the flowering of seeds planted long before. His genius was nurtured by family, by teachers, by books, by culture, and by history itself. His brilliance was not an accident, but the result of a lifelong dialogue between a questioning mind and the world around him. By the time he began to outline the principles that would make him famous, he had already walked a long path shaped by discipline, curiosity, and courage. The thinker who would later announce that the universe is governed by uncertainty had himself been shaped by the uncertainties of life and by the determination to find meaning within them. His early life and education were not just preparation, they were the essence of his identity, the source of the vision that changed the world. As we look back on these years, we see not only the making of a scientist, but the making of a human being whose legacy goes beyond formulas and theories. His youth reminds us that the journey to greatness is never a single moment, but a lifetime of growth, shaped by family, culture, society, and the relentless curiosity that refuses to rest until it finds an answer. The child of 1901 became the thinker of the century because he never stopped asking questions, and because he never stopped believing that knowledge was worth pursuing, no matter how uncertain the answers might be. The story of his early life is, therefore, not just a personal tale but a universal one. It tells us that greatness begins in small moments: curiosity in a classroom, questions at the dinner table, long hours spent reading, quiet walks spent thinking. It tells us that education is not merely about memorizing facts, but about nurturing the courage to think differently. And above all, it tells us that even the greatest scientific revolutions begin in the heart of a child who dares to wonder at the mysteries of the universe. Thus, the early chapters of his life, from childhood to the beginning of his career, stand as a testament to the power of curiosity, discipline, and imagination. Without them, the later chapters would never have been written. Without them, the uncertainty principle might never have been born. And without them, the world of science would not be what it is today. The dawn of the 20th century brought with it one of the most profound shifts in the history of science. For centuries, physics had been a discipline built on certainty, on the conviction that the universe was a vast machine whose every gear and cog could be calculated with perfect precision. The legacy of Newton's laws and Maxwell's equations had given humanity confidence that with enough observation and mathematics, the behavior of the cosmos could be predicted like the ticking of a clock. But by the time the young physicist matured into his career, Cracks had begun to appear in this reassuring vision. It was in this moment of uncertainty that he entered the stage, and it was here that his genius would reshape the future of science. Quantum mechanics was in its infancy when he began his work. Max Planck had startled the world with the idea of quantized energy, introducing the radical notion that energy did not flow smoothly, but was released in discrete packets called quanta. Albert Einstein had further shaken the ground with his explanation of the photoelectric effect, revealing that light itself behaved as if it were made of particles. Niels Bohr had built an early model of the atom, describing electrons orbiting the nucleus like planets circling the sun, though even Bohr's model could not fully explain the strange behaviors observed in laboratories. Physics was entering a revolution, and the young man was among those who would lead it to its most unsettling conclusion. He was drawn deeply into this revolution, not only because of his mathematical gifts, but because of his philosophical temperament. Where others tried to fit quantum discoveries into the comfortable framework of classical ideas, he was willing to let go of old certainties. He sensed that the universe was telling a new story, and he had the courage to listen. His early papers revealed a clarity of thought and a willingness to follow logic even when it led to unsettling truths. He was not afraid of paradox. He embraced it as the starting point of discovery. The heart of his groundbreaking work lay in the strange behavior of electrons, the tiny particles that orbit the nucleus of an atom. Experiments had shown that electrons did not behave like little solid balls following neat trajectories. Instead, they appeared to act sometimes like particles and sometimes like waves, defying the categories of classical physics. This duality puzzled scientists and seemed impossible to reconcile with established laws. The young physicist realized that to make sense of this, one had to abandon the dream of total precision. Instead of imagining electrons as objects with fixed positions and momenta, he proposed that there were fundamental limits to what could be known about them. This insight culminated in what would become his most famous contribution, the principle of uncertainty. In its simplest form, it stated that the more precisely one measures the position of a particle, the less precisely one can know its momentum, and vice versa. It was not a matter of flawed instruments or human error, but a basic feature of reality itself. The universe, at its most fundamental level, was indeterminate. Nature had built uncertainty into its fabric, and no refinement of technology could remove it. This principle was more than a technical detail, it was a philosophical earthquake. For centuries, science had been guided by the dream that with enough effort, everything could be measured and predicted. But here was a law of nature saying that certain knowledge was impossible. At the heart of matter, certainty dissolved into probability. The world was no longer a precise machine but a dynamic interplay of possibilities. It was a truth that defied common sense, yet it explained the strange results that physicists had been observing. The publication of this principle sent shockwaves through the scientific community. Some embraced it with excitement, seeing it as the key to unlocking the mysteries of quantum behavior. Others resisted, clinging to the old dream of determinism. Even Albert Einstein, who had himself launched the quantum revolution, struggled to accept it. Einstein famously declared that God does not play dice with the universe, expressing his discomfort with the idea that chance and probability were woven into the fabric of reality. Yet the young physicist stood firm. He believed that the evidence was undeniable, and that science had to follow truth wherever it led, even if it shattered old beliefs. The power of the uncertainty principle lay not only in its boldness, but in its precision. It could be expressed mathematically, showing the exact limits of measurement at the quantum level. This was not vague speculation. It was a rigorous law, as reliable as Newton's equations or Maxwell's fields. Physicists could now calculate the behavior of particles with unprecedented accuracy, but always in terms of probabilities, never in terms of certainties. The principle became a cornerstone of the new quantum mechanics, shaping theories that would later lead to semiconductors, lasers, nuclear power, and the entire modern digital world. Yet beyond its technical significance, the principle carried a deep philosophical weight. It challenged the human desire for absolute knowledge and forced scientists to accept humility in the face of nature. The young physicist who had grown up reading philosophy now stood at the intersection of science and metaphysics. His principle suggested that reality itself was not a fixed, determined structure but a realm of potentialities, where observation played an active role in shaping outcomes. This idea would later spark debates not only among physicists but among philosophers, theologians, and thinkers in every field. In the universities of Europe, his lectures became legendary. He spoke with clarity and passion, explaining the abstract mathematics of quantum mechanics in ways that revealed their deep meaning. Students remembered his ability to connect equations with the profound questions of existence. To hear him describe uncertainty was not merely to learn physics, it was to glimpse a new vision of the universe. He was not simply teaching science, he was reshaping the way humanity thought about reality itself. But these years were not without struggle. The revolutionary nature of his ideas often brought him into conflict with colleagues who resisted change. Heated debates raged at conferences and in scientific journals. He found himself at the center of controversies, his principle attacked, defended, and endlessly discussed. Yet he remained calm, convinced that the truth of the mathematics and the evidence of experiments would prevail. Over time, the principle gained acceptance, not because of persuasion, but because it worked. It explained results that no other theory could, and it opened pathways to new discoveries. It is striking to consider how his temperament prepared him for this role. The boy who had once been fascinated by philosophy and poetry was now a man who could stand calmly in the storm of intellectual revolution. He did not demand certainty from the world, and so he was able to see the beauty in uncertainty. Where others saw chaos, he saw order of a new kind, an order built not on determinism but on probability, not on rigid predictability but on elegant patterns of chance. This vision was as much philosophical as it was scientific, and it reflected the depth of his character. The principle of uncertainty quickly spread beyond the narrow world of physics. Writers, artists, and thinkers began to use it as a metaphor for the human condition. In an age marked by wars, upheavals, and the collapse of old certainties, the idea that uncertainty was fundamental resonated deeply. His discovery became a symbol of modernity itself, capturing the spirit of a century that had learned to question, to doubt, and to embrace ambiguity. As the principle gained recognition, his reputation soared. He became a central figure in the community of quantum physicists alongside Bohr, Schrödinger, Dirac, and others. Yet he never sought fame for its own sake. For him, the recognition was secondary to the joy of discovery, the thrill of understanding something new about the universe. His humility, combined with his brilliance, made him a respected and admired figure among his peers. Even as he celebrated the acceptance of his principle, he continued to explore its implications. He was fascinated by the role of the observer in quantum mechanics, the way that measurement itself seemed to shape reality. This led him into profound discussions with Bohr and others about the meaning of quantum theory. Their debates were not mere academic quarrels, they were philosophical battles about the nature of truth. He argued with patience and rigor, always seeking clarity, always willing to refine his ideas. These discussions became legendary, shaping the foundations of quantum interpretation for decades to come. What emerges from this period is a portrait of a man who was not only a scientist, but a thinker in the deepest sense. He did not shy away from the unsettling implications of his discoveries. Instead, he embraced them, confident that truth, however strange, was more valuable than comfort. In doing so, he gave humanity not only a scientific principle but a lesson in courage, the courage to accept uncertainty, the courage to live with limits, the courage to see beauty in the unknown. The uncertainty principle did not remain a theoretical curiosity confined to the notebooks of physicists. As the years passed, it became the cornerstone of a new worldview, a way of understanding nature that challenged the deepest assumptions of humanity. To grasp its impact, one must imagine the intellectual climate of the early 20th century. Science had always promised certainty, precision, and prediction. Now, with one stroke, a young physicist had declared that nature itself imposed boundaries on what could be known. This was not the failure of human intelligence, but the very essence of reality. It was as if the universe itself was whispering a secret, that mystery is not an obstacle to knowledge, but part of its very structure. The idea unsettled many, none more than Albert Einstein. For Einstein, the universe was rational, elegant, and ultimately deterministic. He admired the mathematical beauty of quantum theory, but he resisted its philosophical implications. The notion that particles could exist in states of probability until observed, and that fundamental properties like position and momentum could not both be known with precision, struck him as incomplete. He insisted that God does not play dice, refusing to believe that chance was woven into the fabric of creation. This disagreement led to one of the most famous debates in the history of science, the exchanges between Einstein and the physicist who had introduced uncertainty. At conferences and in private conversations, the two men argued passionately. Einstein presented thought experiments designed to show that quantum mechanics must be flawed, while his opponent countered with reasoning and mathematics that defended the theory. Niels Bohr often joined these debates, standing firmly on the side of uncertainty. These discussions were not polite disagreements but intense intellectual battles, where the greatest minds of the age wrestled with the meaning of reality itself. The young physicist, though respectful of Einstein's genius, refused to retreat. He believed that the mathematics of quantum theory, strange as it seemed, revealed a deeper truth than classical determinism could ever provide. Over time, experiment after experiment confirmed the validity of the uncertainty principle. Physicists built increasingly precise instruments, testing whether the limits it described could be overcome. Every attempt only reinforced the principle's accuracy. It was not a temporary gap in knowledge, but a permanent feature of the quantum world. The more evidence accumulated, the clearer it became that Einstein's dream of complete determinism was slipping away. Reality was not a clockwork machine but a dance of probabilities. This realization changed the direction of science. The uncertainty principle became a guiding concept in fields as diverse as particle physics, chemistry, and even information theory. It explained the stability of atoms, showing why electrons did not collapse into the nucleus. It helped describe the behavior of particles in accelerators, laying the groundwork for discoveries that would eventually reveal quarks and other fundamental components of matter. It also influenced the design of technologies that became central to modern life, from transistors to lasers to quantum computers. What had begun as a radical idea on paper became a practical tool, shaping the technological landscape of the modern world. Yet the reach of uncertainty was not confined to laboratories. Philosophers, writers, and artists seized upon it as a metaphor for the human condition. In a century marked by wars, revolutions, and shifting identities, the idea that uncertainty was fundamental resonated deeply. Writers compared it to the unpredictability of history, poets to the mysteries of the soul, and psychologists to the complexities of the human mind. The principle of uncertainty became more than a scientific law. It became a symbol of modern existence, a reminder that life itself cannot be reduced to simple formulas. The physicist himself was aware of this broader influence, but he remained committed to the discipline of science. He did not seek to turn his principle into a philosophy of life, yet he recognized its implications. He often spoke about the humility required of scientists, the necessity of accepting limits, and the importance of acknowledging that nature was always greater than human comprehension. This humility gave him a quiet authority, a sense that he was not simply defending a theory, but voicing a truth about the human relationship with the universe. As his career advanced, he continued to refine his ideas, exploring the mathematical and experimental frontiers of quantum mechanics. He collaborated with colleagues, advised students, and helped build the intellectual infrastructure of modern physics. His influence spread across Europe and beyond, shaping institutions and inspiring younger generations. Many of his students would go on to make significant contributions themselves, carrying forward the spirit of inquiry he had instilled in them. In time, the debates over uncertainty shifted. What had once been controversial became accepted, not because the opponents had been silenced, but because reality itself spoke in its favor. The principle had proven indispensable, a law of nature as reliable as gravity or thermodynamics. And yet, even as it became established, it remained mysterious, a reminder that human knowledge is always partial. Unlike other laws that offer certainty, this law offered a paradox, that certainty itself has boundaries. It was both empowering and humbling, both a triumph of science and a call to humility. The impact of this principle on society cannot be overstated. By challenging the dream of absolute knowledge, it reshaped how people thought not only about physics but about knowledge itself. It inspired new approaches in philosophy, influenced debates in theology, and even entered the language of everyday life. To speak of uncertainty became a way of acknowledging complexity, ambiguity, and openness. In this sense, the principle transcended science, becoming part of culture, part of how humanity understood itself in the 20th century. The physicist lived long enough to see his principle become enshrined in textbooks, taught to generations of students as one of the pillars of modern science. He saw its applications spread into technology and its echoes resonate in philosophy. Yet for him, the true satisfaction was never in recognition or fame. It was in the pursuit of truth, in the act of discovery itself. He had followed his curiosity from childhood, through education, into the heart of science, and had uncovered a principle that forever changed the way humans see the universe. As he reflected later in life, he often spoke with modesty about his work. He did not claim to have solved the mysteries of existence, only to have glimpsed one part of its deeper order. The uncertainty principle was, in his mind, not the end of knowledge but a doorway to new questions. It reminded him, and all who studied it, that science is a journey without final answers, a dialogue with nature that always reveals more than it conceals. In the end, the groundbreaking work of this physicist was not just a scientific achievement, but a human one. It required courage to let go of old certainties, imagination to see new possibilities, and perseverance to defend an idea against resistance. His discovery continues to guide science into the 21st century, as researchers explore quantum computing, cryptography, and the mysteries of entanglement. Each of these fields rests on the foundation he laid, the recognition that uncertainty is not a weakness, but a fundamental truth. The thinker who shaped quantum uncertainty gave humanity more than a principle, he gave a new way of seeing. He taught that reality is not a fixed structure, but a dynamic interplay of possibilities, that knowledge has limits, and that within those limits lies the beauty of discovery. His work reminds us that certainty is not the ultimate goal of science, understanding is, and understanding, as he showed, begins with the courage to embrace the unknown. The story of the uncertainty principle stands not merely as a scientific discovery, but as a revolution in human thought, a turning point that redefined the very meaning of knowledge. For centuries, the pursuit of science had been guided by the conviction that nature was ultimately transparent to the human mind. If one observed carefully enough, measured precisely enough, and calculated diligently enough, then every law of the universe could be revealed, every motion predicted, every hidden truth exposed. From the celestial mechanics of Newton to the rational order of Maxwell's equations, the guiding vision was that the universe was a perfect machine, unfolding with absolute predictability. Yet, in the early decades of the 20th century, this vision collapsed under the weight of a single principle, the principle of uncertainty. At its core, the uncertainty principle announced something profoundly unsettling, that there are natural limits to what can be known. It was not a matter of instruments being too weak or humans being too clumsy. It was a law of nature itself. If one tried to measure the position of an electron with great precision, then its momentum, the measure of its motion, slipped into indeterminacy. If one fixed the momentum with clarity, then the position blurred into uncertainty. The more one tried to pin reality down, the more it danced away. This was not a technical inconvenience. It was the fundamental way the universe operated. The revolutionary nature of this principle becomes clear when placed against the backdrop of scientific tradition. Classical physics had been built on determinism, the belief that if the initial conditions of any system were known with complete precision, then the future could be predicted with certainty. Laplace, a mathematician of the 19th century, had imagined an intelligence so vast and powerful that, if it knew the positions and velocities of every particle in the universe, it could calculate the entire future and reconstruct the entire past. This vision of absolute predictability was the crown jewel of classical science. But the uncertainty principle shattered it. It declared that even in theory, such knowledge was impossible. Nature had drawn a line beyond which even the sharpest intelligence could not see. The implications of this were staggering. Suddenly, the universe was no longer a predictable clockwork, but a sea of probabilities. Particles did not follow precise paths, but existed in clouds of possibilities. Events could no longer be described with absolute certainty, only with likelihoods. Science had moved from the realm of certainty into the realm of chance. To many, this sounded like a betrayal of the scientific spirit. Was not science meant to banish uncertainty, to replace doubt with knowledge? But the revolutionary genius of the uncertainty principle was to show that uncertainty was not the enemy of knowledge. It was, in fact, its foundation. For the scientists of the time, grappling with this idea was a journey through confusion and resistance. Einstein, who had himself helped create quantum theory, recoiled at the principle's radicalism. He was famous for insisting that God does not play dice with the universe, refusing to accept that chance was at the heart of reality. To him, the uncertainty principle was not the final word, but an incomplete description of a deeper, deterministic order yet to be discovered. His debates with Niels Bohr and Werner Heisenberg became legendary, as they wrestled with the meaning of this principle in conferences that shaped the history of science. Bohr defended the uncertainty principle with fervor, arguing that it revealed a profound truth about the limits of observation. To measure was not to stand apart from nature, but to interact with it. The very act of observing disturbed what was observed. The universe could not be separated from the act of measurement. In this view, uncertainty was not a flaw but a window into the fundamental relationship between humans and the cosmos. Heisenberg himself embraced this vision, recognizing that uncertainty was not merely a technical point, but a philosophical revolution. This revolution spread far beyond the walls of laboratories. It redefined the concept of reality. If particles existed only in probabilities until observed, then what was the nature of existence itself? Was reality fixed and waiting to be discovered, or did it come into being through interaction? Philosophers seized upon these questions, exploring their implications for knowledge, consciousness, and truth. The uncertainty principle became a bridge between science and philosophy, reshaping centuries-old debates about determinism, free will, and the nature of being. For the ordinary citizen, the principle seeped into culture in subtler ways. Writers used it as a metaphor for ambiguity, for the impossibility of complete understanding. Artists drew inspiration from its suggestion of fluidity and indeterminacy. In a world shaken by war, revolution, and rapid social change, the idea that uncertainty lay at the heart of reality resonated deeply. The principle became a symbol of modernity itself, capturing the sense that the old certainties had vanished and a new, more complex world had emerged. But the revolutionary force of the uncertainty principle was not merely philosophical or cultural. It had direct consequences for the practice of science. It reshaped physics, guiding the development of quantum mechanics into a coherent theory that could describe atomic and subatomic phenomena with astonishing accuracy. It explained why atoms were stable, why matter had structure, and why chemistry was possible. Without the uncertainty principle, electrons would spiral into nuclei, atoms would collapse, and the world as we know it would not exist. Far from undermining science, the principle saved it, providing the key to understanding the stability of matter. The principle also inspired new technologies that transformed human life. Quantum mechanics, built on the foundation of uncertainty, gave rise to semiconductors, lasers, and nuclear power. In the 21st century, it has become the bedrock of emerging fields like quantum computing and quantum cryptography. Every time a smartphone processes information or a laser scans a barcode, it bears silent testimony to the revolutionary power of uncertainty. And yet, perhaps the most enduring revolution was psychological. The uncertainty principle taught humanity humility. It reminded scientists and citizens alike that there are limits to human knowledge, boundaries set not by ignorance, but by nature itself. This was a radical departure from the arrogance of earlier centuries, when science had promised to master and control the universe. Instead, uncertainty whispered a different message, that the universe is not something to be conquered, but something to be understood with reverence, patience, and respect. Even today, nearly a century after its first formulation, the uncertainty principle continues to challenge, inspire, and provoke. Scientists still debate its deepest meaning. Some explore interpretations of quantum mechanics that seek to restore determinism in hidden ways, while others embrace the principle as the final word. Philosophers continue to ponder its implications for reality, and theologians sometimes find in it an echo of mystery. The principle remains alive, not as a relic of history, but as a living idea, shaping the frontier of thought. When the principle first appeared, it seemed to many like a limitation, a negative boundary that cut off the dream of complete knowledge. But over time it revealed itself to be a gift, a gateway to new possibilities. By accepting uncertainty, science unlocked doors that would have remained closed under the tyranny of determinism. It is in the spaces of uncertainty that creativity, discovery, and innovation thrive. The principle that once seemed to constrain knowledge has become its most fertile ground. The revolutionary nature of the uncertainty principle lies, therefore, not only in its scientific content but in its spirit. It transformed the way humanity thinks about knowledge, reality, and itself. It stands as a reminder that truth is not always neat or simple, that the universe is deeper and more mysterious than human imagination can fully grasp. It is a revolution that continues to unfold as each generation of scientists, philosophers, and dreamers wrestles with the meaning of uncertainty. And so, the uncertainty principle endures as one of the great landmarks in the history of ideas. It is not merely a law of physics, but a symbol of the 20th century's intellectual awakening. A moment when humanity learned that to know is not always to control, that to understand is sometimes to accept limits, and that within those limits lies the possibility of wonder. In the sweep of history, few ideas have reshaped the landscape of thought so completely. The uncertainty principle did not just revolutionize science. It revolutionized the very way we see the universe and our place within it. The uncertainty principle did not remain confined to the pages of academic journals. With time, its revolutionary essence seeped into every aspect of human thought, extending far beyond physics, until it became a universal metaphor for the unknown. To grasp the scale of its impact, one must imagine the shifting world of the 20th century, a century in which certainty collapsed not only in science but also in politics, art, and culture. The principle arrived at a moment when humanity was already questioning the foundations of its beliefs, and it provided a language for that uncertainty, a framework for understanding the instability of a rapidly changing world. In the scientific community, the principle marked a clear departure from the ideal of absolute objectivity. No longer could the observer be imagined as a detached spectator, watching the universe unfold from a distance. The observer was now part of the very fabric of the experiment, inseparable from the phenomena being measured. This was more than a technical point. It was a reimagining of the scientific method itself. The act of measurement was no longer neutral. It shaped reality. This realization changed the relationship between humanity and nature. Science was no longer about conquering reality with instruments, but about participating in its unfolding. This revolution created ripples that spread across disciplines. In chemistry, the uncertainty principle explained the structure of atoms and molecules, allowing scientists to predict chemical bonds and reactions. Without it, the periodic table would remain only a list of elements rather than a dynamic map of interactions. In engineering, it laid the foundation for electronics, making possible the transistor, the device that underpins computers, communication, and the digital revolution. In medicine, technologies like MRI scanners rely on principles rooted in quantum mechanics, which in turn are guided by uncertainty. In each case, the principle acted like an invisible hand, guiding innovation, enabling progress, and transforming lives. But the principle's influence was not limited to practical applications. It reached into the deepest questions of philosophy. For centuries, thinkers had debated the nature of free will, determinism, and causality. The classical worldview, with its clockwork universe, suggested that every action was predetermined, that if one could know the initial state of the universe, the entire future was fixed. The uncertainty principle broke that chain, introducing a space for indeterminacy. For some philosophers, this was a vindication of human freedom, a scientific confirmation that the universe was not rigidly fated but open to possibilities. For others, it was an unsettling reminder that the foundations of reality were less stable than imagined. Even theology was touched by the principle. In religious debates, uncertainty was sometimes invoked as evidence that the universe contained mystery beyond human comprehension, a space where faith could dwell. Others saw it as undermining traditional ideas of divine order, replacing certainty with probability. Whatever the interpretation, it was clear that this principle had moved beyond physics and entered the realm of existential questions. The cultural impact was equally profound. Artists and writers of the modernist era embraced uncertainty as a theme. Novels began to experiment with fragmented narratives, poems with ambiguity, and paintings with abstraction. The certainty of classical forms gave way to experimentation and openness. The uncertainty principle provided a scientific echo to this artistic revolution, as if both science and art were responding to the same spirit of the age, a recognition that reality was no longer fixed, but fluid, complex, and shifting. The principle also had psychological consequences. For individuals, it symbolized the limits of control. In an era marked by world wars, economic crises, and political upheavals, people found in the uncertainty principle a reflection of their lived reality. Just as particles could not be fully pinned down, so too the future of nations and individuals seemed unpredictable. The principle became a scientific metaphor for anxiety and hope alike, a reminder that certainty was an illusion, but that within uncertainty lay the possibility of change. Within the scientific world, the debates did not end. Some physicists sought to reinterpret the uncertainty principle in ways that restored determinism, suggesting that hidden variables might exist beneath the surface, giving the universe an unseen order. Others, like Bohr and Heisenberg, resisted this view, insisting that uncertainty was not a veil covering deeper truth, but the truth itself. These debates gave rise to different interpretations of quantum mechanics, the Copenhagen interpretation, the many worlds hypothesis, and others, each wrestling with the meaning of uncertainty. To this day, physicists continue to argue about what the principle really means, even as they rely on it to make accurate predictions. The revolutionary power of the uncertainty principle lies not only in its scientific validity, but in its durability. Unlike many theories that fade with time, it has remained central for nearly a century, its implications still unfolding. In the 21st century, new technologies like quantum computing are once again pushing the boundaries of uncertainty. Quantum bits, or qubits, rely on the strange properties of superposition and entanglement, phenomena directly tied to the uncertainty principle. These machines promise to revolutionize computing, solving problems beyond the reach of classical systems. Here, uncertainty becomes not a limitation but a resource, something to be harnessed for creativity and innovation. Beyond technology, the principle continues to shape how humans think about knowledge itself. It reminds us that knowledge is always partial, that every answer leads to new questions, and that certainty is not the goal of science. Instead, science is a dialogue with nature, a process of continual discovery in which uncertainty is not an obstacle but a companion. This message is more relevant than ever in a world facing complex challenges, from climate change to artificial intelligence, where certainty is rare and humility is essential. As a revolutionary concept, the uncertainty principle also reshaped the image of the scientist. No longer was the scientist the master of knowledge, the one who could predict and control with absolute precision. Instead, the scientist became a seeker, a participant in a larger mystery, aware of the limits of reason but undeterred by them. This shift brought science closer to philosophy and even to art, uniting them in a shared recognition of the complexity of reality. The enduring lesson of the uncertainty principle is that limits are not failures. They are opportunities. By showing that certain knowledge is impossible, the principle opened new paths of exploration. By denying determinism, it affirmed creativity. By embracing uncertainty, it revealed a universe richer and more mysterious than any mechanical vision could offer. The thinker who gave this principle to the world transformed more than physics. He transformed the human imagination. His insight continues to shape not only the way we build machines and conduct experiments, but the way we understand ourselves and our place in the cosmos. The uncertainty principle is not just a law of science, it is a law of life, reminding us that the unknown is not a void to be feared, but a field of possibilities to be explored. As the decades pass, the principle continues to echo. Each new discovery in physics, from quantum entanglement to the search for a theory of everything, must reckon with uncertainty. Each new technology, from encryption to nanoscience, depends upon it. Each new philosophical reflection on knowledge and reality bears its imprint. The revolution it began is still unfolding, still challenging, still inspiring, and so, the uncertainty principle remains one of the most powerful ideas ever conceived by the human mind. It turned science from a search for final answers into a journey of endless questions. It transformed knowledge from certainty into exploration. It taught that to live in a universe of uncertainty is not to be lost, but to be free, to imagine, to create, to discover. The revolution it sparked was not one moment in history, but a continuing story, one that will shape human thought for centuries to come. When the uncertainty principle was first introduced, it was not only physicists who felt its tremors. The idea that reality itself contained irreducible limits shook the foundations of philosophy, psychology, and human thought as deeply as it shook the laboratories of science. For centuries, philosophers had pursued certainty, building systems of logic and reason designed to provide stable truths. Science, since the Enlightenment, had seemed to confirm that quest, offering laws of motion, gravity, and electromagnetism that brought order to the chaos of the natural world. But with the arrival of quantum uncertainty, that centuries-long confidence faltered. It became clear that human thought could no longer rely on the promise of absolute knowledge. Instead, it had to confront the possibility that uncertainty was woven into the very fabric of existence. Philosophically, this principle challenged determinism. In the classical worldview, every effect had a cause, every movement followed inevitably from what came before. Human freedom was often treated as an illusion in a mechanical universe where the future was already encoded in the past. With uncertainty, this chain of strict determinism was broken. The world was no longer a rigid machine, but a field of probabilities. This gave philosophers new ground to argue for free will and creativity, for the idea that human choices were not merely pre-written outcomes of physical laws but part of a universe open to possibilities. At the same time, It raised questions about whether freedom was truly free or only another form of unpredictability. The debate revived old arguments about causality, destiny, and moral responsibility, now infused with the language of modern physics. The principle also reshaped epistemology, the study of knowledge itself. If science could no longer claim to offer complete and absolute truths, what did that mean for the very definition of knowledge? Philosophers began to see knowledge not as a final possession, but as an evolving process, a dialogue between humans and nature. Truth became provisional, always subject to refinement, always limited by perspective. This realization did not weaken the value of science, it deepened it, giving it humility and flexibility. Instead of offering final answers, science was reimagined as a method of continual questioning, where uncertainty was not a defect but an essential companion. In psychology, the principle found a surprising echo. Human beings had always struggled with the unknown, with anxiety, with the inability to predict the future. The uncertainty principle seemed to mirror this existential condition. It became a metaphor for the limits of human control, a scientific validation of the idea that life cannot be completely planned or predicted. Some psychologists even suggested that learning to accept uncertainty was key to mental health, just as scientists had to accept it to make progress. The parallel between the quantum world and the human mind enriched both science and psychology, creating a shared language of humility, adaptability, and resilience. Writers, too, seized upon the philosophical implications. The uncertainty principle appeared in literature, sometimes explicitly, more often as a symbol of ambiguity, doubt, or complexity. In modernist and postmodernist works, characters often faced worlds that seemed unstable, fragmented, and unpredictable, mirroring the new physics. In art, abstract expressionism and other movements embraced indeterminacy, leaving room for chance, spontaneity, and openness. The principle's impact on human thought was thus not only theoretical but cultural, shaping the very way people expressed their experience of reality. Religion and theology also felt the resonance of uncertainty. For some believers, the principle opened space for mystery and faith, showing that science itself acknowledged limits and could not explain everything. For others, it raised troubling questions. If the universe is governed by probabilities, what does that say about divine order or providence? These debates showed how deeply the principle penetrated human thought, becoming a crossroads where science, philosophy, and spirituality met. Perhaps the most profound impact, however, was existential. Humanity, faced with the uncertainty principle, had to accept that reality is not completely knowable. This realization fostered a new sense of humility, but also a new kind of courage. To live in an uncertain universe is to live without guarantees, but also with the possibility of freedom, creativity, and discovery. The principle taught that certainty is not the foundation of life, but that uncertainty itself can be fertile ground. It invited people to imagine the unknown not as a threat, but as a field of infinite possibilities. In the long view of history, the uncertainty principle represents a turning point in human thought as significant as the Copernican revolution or Darwin's theory of evolution. Each of these breakthroughs forced humanity to reconsider its place in the cosmos first, by realizing Earth was not the center of the universe, then by realizing humans were not separate from nature but part of its evolutionary story, and now, by realizing that certainty itself is not the ultimate structure of reality. The uncertainty principle reminded humanity that mystery is not something to be banished, but something to be embraced, that true wisdom lies not in control but in understanding the limits of control. As the 20th century unfolded and gave way to the 21st, this lesson became ever more relevant. In a world marked by global change, rapid technology, and constant unpredictability, the philosophical lesson of quantum uncertainty speaks with new urgency. Just as scientists learn to thrive within limits, humanity must learn to live with ambiguity, to act with wisdom in the face of incomplete knowledge, to find courage in uncertainty. Thus, the impact of quantum uncertainty on philosophy and human thought has been profound and enduring. It has reshaped ideas of freedom and determinism, redefined knowledge, inspired art and literature, challenged theology, and offered a new vision of human existence. It has taught that uncertainty is not the opposite of knowledge, but its deepest condition, that within uncertainty lies creativity, possibility, and life itself. When the uncertainty principle was first introduced, it did not simply settle into the body of scientific knowledge as a quiet discovery. Instead, it ignited a storm of debates and controversies that lasted for decades, dividing great minds and sparking one of the most remarkable intellectual battles of the 20th century. The principle, simple in its mathematical form, carried implications that shook the very foundations of science and philosophy. Could the universe truly be indeterminate, governed by probabilities rather than precise laws? Could human knowledge truly be limited by nature itself, not just by human weakness? For many, these questions were intolerable, and they resisted with passion and conviction. At the center of these debates stood Albert Einstein. Though he had himself contributed to the birth of quantum mechanics, he found the uncertainty principle profoundly unsettling. Einstein had grown up in the tradition of classical physics, where the universe was rational, lawful, and deterministic. Every event had a cause, and with enough information, the future could be predicted with certainty. The uncertainty principle struck at the heart of this vision, suggesting that even in principle, one could not know everything. To Einstein, this was not science but surrender. He famously declared, "God does not play dice with the universe," capturing his refusal to accept randomness as a fundamental feature of reality. Against him stood Niels Bohr and Werner Heisenberg, the defenders of the new quantum view. Bohr argued that Einstein was clinging to an outdated notion of reality, that the uncertainty principle revealed a deeper truth. Reality is not independent of observation, and knowledge is always limited by the interaction between observer and observed. To Bohr, uncertainty was not a flaw in science, but the very essence of the quantum world. Heisenberg, too, defended the principle fiercely, showing through mathematics and experiments that Einstein's objections could not overturn its validity. The debates between Einstein and Bohr became legendary, unfolding in conferences such as those held at Solvay, where the greatest scientists of the era gathered. These were not polite academic disagreements, but passionate struggles over the meaning of reality itself. Einstein proposed thought experiments designed to expose weaknesses in the uncertainty principle. Could one not, by clever arrangements, measure both position and momentum more precisely than Heisenberg allowed? Each time, Bohr countered with equally clever reasoning, showing that Einstein's challenges only reinforced the truth of uncertainty. The intellectual duel between the two men became one of the defining dramas of modern science. Yet the controversy extended beyond physics into philosophy. Some philosophers welcomed the uncertainty principle as a liberation from the mechanical determinism of the 19th century. They saw in it a scientific basis for freedom, creativity, and indeterminacy. Others found it deeply troubling, a collapse of rationality into chaos. If science itself admitted uncertainty, what could be said about human knowledge in general? Could philosophy still claim to search for truth, or was all thought now condemned to relativism and ambiguity? These questions reverberated through academic circles, fueling heated debates that blurred the lines between science and philosophy. The controversy also revealed deep differences in temperament and worldview. For Einstein, the ideal of science was clarity, simplicity, and order. He could not accept a universe built on chance. For Bohr, science was about humility before nature, about accepting limits and embracing paradox. He could live with uncertainty, because he believed it was the price of honesty in the face of reality. This clash of visions was as much about personality as it was about equations, about the human need for certainty versus the human capacity to live with mystery. In time, experiments settled the scientific debate. Tests of quantum mechanics confirmed again and again that the uncertainty principle was correct. Einstein's dream of hidden variables, A deeper determinism beneath the surface could not be supported by evidence. Later experiments, such as those inspired by John Bell in the 1960s and 70s, showed that no local hidden variable theory could reproduce the predictions of quantum mechanics. Reality itself seemed to demand uncertainty. The controversy was not resolved by persuasion, but by the stubborn voice of nature itself. Still, the philosophical questions remained. Even if the uncertainty principle was scientifically valid, what did it mean for the nature of reality? Did particles exist in definite states before being observed, or did observation bring them into being? Was the uncertainty principle a statement about human knowledge, or about the universe itself? These questions continue to divide philosophers and physicists alike. Different interpretations of quantum mechanics, the Copenhagen interpretation, the many worlds interpretation, Bohmian mechanics, each offer different answers. The controversy has never fully ended, it has only evolved, branching into new forms as science advances. The debates surrounding the uncertainty principle also had cultural significance. In a century scarred by war, upheaval, and rapid change, the controversy mirrored the broader human struggle between the desire for stability and the acceptance of uncertainty. Einstein's resistance reflected the yearning for order, for a rational universe that could be trusted. Bohr's acceptance reflected the courage to face a world without guarantees. Both voices found resonance in society, and the debates became more than scientific. They became symbolic of the choices humanity faced in an uncertain age. In the end, the controversies surrounding the uncertainty principle reveal something essential about the nature of knowledge. They show that science is not a smooth progression of facts, but a human struggle full of passion, doubt, and resistance. They remind us that even the greatest minds can disagree, that truth is often revealed not in consensus but in conflict. And they highlight the courage required to accept a universe that defies human expectations. The uncertainty principle triumphed, but it triumphed not by silencing debate, but by surviving it, by withstanding every challenge and growing stronger in the process. The controversies it inspired enriched science and philosophy alike, forcing humanity to confront its assumptions and expand its vision. In that sense, the debates were not obstacles, but part of the revolution itself, essential to the transformation of human thought. The sixth keynote focuses on the role of uncertainty in shaping modern physics and technology, a theme that demonstrates how a single principle, born out of mathematical reasoning and experimental insight, transformed not only the way scientists view the universe, but also the tools and technologies that define everyday life. When Werner Heisenberg introduced the uncertainty principle, many considered it a philosophical limitation, a strange restriction on knowledge rather than a useful element of science. Yet, as the decades unfolded, uncertainty proved to be more than an abstract boundary. It became a guiding concept that opened doors to entire fields of modern physics and underpinned technologies that now sustain the modern world. In physics, the uncertainty principle shifted the way scientists approached fundamental questions. Before its arrival, the dream of physics had been absolute predictability. With Newtonian mechanics, one could imagine a universe like a great clockwork, where every motion was determined by initial conditions and natural laws. After uncertainty entered the scene, that vision collapsed. Instead, physicists found themselves in a probabilistic universe, where the behavior of particles could only be predicted in terms of likelihoods. This change was not a defeat but a revolution. It pushed scientists to create new methods of description, new mathematical formalisms, and entirely new ways of thinking about nature. Quantum mechanics itself became possible because of the uncertainty principle. It ensured that electrons around an atom could never spiral into the nucleus, because they could not simultaneously have precisely defined positions and momenta. This uncertainty stabilized the atom, making the structure of matter as we know it possible. Without uncertainty, chemistry and biology would collapse, and the very fabric of the world would be unimaginable. Thus, What appeared at first as a limitation turned out to be the very condition for the existence of stable matter and life itself. But the principle did more than explain why atoms exist. It also guided the exploration of nuclear physics, particle physics, and cosmology. In nuclear reactions, uncertainty determines the behavior of particles tunneling through barriers, a process without which nuclear fusion, the reaction that powers the sun, would not occur. In particle accelerators, uncertainty governs the way collisions unfold, shaping the interpretation of high-energy experiments. In cosmology, uncertainty plays a role in the earliest moments of the universe, where quantum fluctuations in the energy field became the seeds of galaxies and cosmic structures. Every layer of modern physics, from the smallest particles to the largest cosmic scales, bears the mark of uncertainty. Alongside the theoretical advances, uncertainty also shaped technology in profound ways. Modern electronics, for example, depend on semiconductors, which operate based on quantum principles rooted in uncertainty. The transistors that power computers and smartphones rely on the probabilistic behavior of electrons within materials. Without embracing uncertainty, engineers could never have designed the microchips that run the digital age. Similarly, quantum tunneling, a direct consequence of uncertainty, gave birth to devices such as the tunnel diode and the scanning tunneling microscope, the latter capable of imaging individual atoms with breathtaking precision. The uncertainty principle also laid the foundation for quantum computing, one of the most revolutionary technological pursuits of the 21st century. Traditional computers manipulate bits that are either 0 or 1, but quantum computers use qubits, which can exist in superpositions of states, governed by uncertainty and entanglement. The potential power of such machines lies precisely in their ability to exploit quantum uncertainty rather than avoid it, solving problems that would take classical computers millennia to compute. Here, what once seemed like a limitation has become a source of unprecedented possibility. Beyond computing, uncertainty has reshaped communication through quantum cryptography. Because of the uncertainty principle, any attempt to measure or eavesdrop on a quantum communication channel disturbs the system and reveals the intrusion. This property has inspired secure communication systems that could one day protect data against even the most powerful attacks. Once again, uncertainty has been transformed from a philosophical puzzle into a practical tool of immense value. The role of uncertainty in technology also extends into medicine and imaging. Techniques like magnetic resonance imaging, MRI, rely on quantum mechanical principles tied to uncertainty, allowing doctors to peer inside the human body with stunning clarity and without invasive procedures. Medical technologies that save lives every day are, in part, gifts of the uncertainty principle. Yet the influence of uncertainty goes beyond physics and engineering. It has shaped the way science itself is practiced. By forcing scientists to accept limits and probabilities, it encouraged the development of statistical methods, error analysis, and probabilistic models across disciplines. From climate science to genetics, researchers embrace uncertainty not as a weakness, but as a reality of nature, building models that can make reliable predictions within bounds of probability. The very way science communicates, using confidence intervals, error bars, and probabilities, is a reflection of the philosophical shift brought by Heisenberg's insight. Uncertainty also became a bridge to other fields, inspiring thinkers in economics, psychology, and even art. In economics, models of risk and unpredictability drew inspiration from quantum uncertainty, emphasizing the role of chance and probability in human affairs. In psychology, the recognition of limits to perception and knowledge found parallels in the uncertainty principle, reshaping ideas about human cognition. Artists and writers, too, found resonance in the idea that reality is not fixed but fluid, not absolute but probabilistic. The principle transcended science, becoming a metaphor for the human condition in a century defined by rapid change and instability. As technology continues to evolve, the role of uncertainty only grows more central. The development of quantum technologies, computing, sensing, communication, represents not just a scientific advance but a technological revolution. Nations compete to harness uncertainty for strategic advantage, investing billions into quantum research. The same principle that once sparked philosophical debates now drives economic, military, and technological progress on a global scale. In reflecting on the role of uncertainty, one sees a pattern that defines the history of science itself. What begins as a puzzle, even a threat to established order, can become a source of creativity and innovation. The uncertainty principle exemplifies this transformation more than almost any other discovery. It reminds humanity that limits can be opportunities, that constraints can spark revolutions, and that knowledge often grows not by erasing boundaries, but by learning to live within them. Thus, the uncertainty principle stands as both a scientific truth and a cultural force. It shaped modern physics by opening new realms of inquiry and shaped technology by enabling inventions that now define the modern world. It continues to shape the future, driving quantum revolutions yet to fully unfold. From the smallest particles to the largest technologies, uncertainty reigns not as a shadow, but as a guiding light, reminding humanity that even in a universe where certainty is impossible, progress is inevitable. The seventh keynote is about the enduring legacy of uncertainty in science and human thought, a theme that stretches beyond physics and touches the very foundations of how humanity understands itself and its place in the cosmos. When Werner Heisenberg introduced the uncertainty principle in 1927, he could not have known that his idea would echo across disciplines, cultures, and generations, shaping not only the trajectory of science, but also the philosophy, art, and worldview of the modern age. What began as a mathematical formulation about the impossibility of knowing position and momentum simultaneously became a symbol of the human encounter with the unknown, an emblem of the 20th century's confrontation with limits and complexity. In science, the legacy of uncertainty is clear. It redefined the goals and methods of physics, moving away from the dream of total determinism toward an acceptance of probability and approximation. The recognition that knowledge has limits did not weaken science but strengthened it, making it more realistic and resilient. Today, no scientist expects absolute precision in describing natural phenomena. Instead, error margins, confidence intervals, and probabilistic models are accepted as essential tools. This attitude, born from Heisenberg's principle, has spread beyond physics into biology, chemistry, climate science, and even artificial intelligence. Everywhere, uncertainty is no longer an enemy but a companion, guiding the way knowledge is pursued and communicated. The principle also changed how humanity conceives of nature itself. The clockwork universe of Newton, where every effect followed inevitably from every cause, gave way to a vision of reality that is flexible, dynamic, and sometimes unpredictable. This shift in worldview was as significant as the Copernican revolution. It altered the human sense of order, revealing a universe where chance and indeterminacy play an irreducible role. For many, this was unsettling, for it suggested that certainty and control are illusions. Yet, for others, it was liberating, opening space for creativity, spontaneity, and freedom within the scientific picture of the world. The philosophical legacy of uncertainty has been profound. Thinkers wrestled with its implications for determinism, causality, and free will. If even the smallest particles do not follow predetermined paths, what does that mean for the larger structures of life and thought? Does uncertainty at the quantum level translate into uncertainty in human existence? These questions inspired debates that continue to this day, with philosophers using the uncertainty principle as a metaphor for the limits of human reason and the openness of the future. It became an intellectual bridge between physics and philosophy, showing how discoveries in science can transform the deepest categories of human thought. In art and literature, uncertainty resonated with the spirit of the 20th century, an era marked by upheaval, war, and change. Writers and poets used it as a metaphor for the instability of modern life, for the collapse of certainties that once anchored culture and society. Painters in the modernist and postmodernist traditions embraced fragmentation and indeterminacy, reflecting the same sensibility that the uncertainty principle expressed in science. Filmmakers and dramatists, too, found in uncertainty a theme that captured the tensions of their age. The principle thus transcended the laboratory, becoming part of the cultural imagination, a symbol of the age of relativity and quantum revolution. Its legacy is also visible in ethics and human self-understanding. The recognition of limits in knowledge encouraged humility, a reminder that no matter how advanced technology becomes, there will always be mysteries that escape control. This humility is vital in an age of immense scientific power, where humanity can split the atom and alter the climate. The uncertainty principle reminds us that knowledge is always partial and decisions must be made with awareness of risks and unknowns. In this way, it serves not only as a scientific truth but as a moral lesson about the human condition. In the realm of technology, the legacy of uncertainty is ongoing. It has driven the development of quantum technologies that will define the future. Quantum computers, quantum sensors, and quantum communication systems. These technologies are not attempts to escape uncertainty, but to harness it, to transform what once seemed a barrier into a resource. The principle that once symbolized limits now fuels innovation. Its legacy is not only intellectual but practical, woven into the fabric of daily life through devices and systems that rely on quantum mechanics. Culturally, the uncertainty principle continues to shape how people talk about knowledge and truth. Politicians, philosophers, and even ordinary conversations sometimes invoke uncertainty as a reminder of complexity, nuance, and the impossibility of simple answers. It has become a metaphor for living in a world that is fast-changing, interconnected, and unpredictable. Just as the principle revolutionized science, it has also revolutionized the language with which people describe reality itself. The enduring legacy of uncertainty is, above all, a reminder of the richness of human inquiry. It shows that limits are not failures but opportunities. By accepting that some things cannot be known with absolute precision, humanity has discovered deeper layers of reality and built technologies unimaginable a century ago. The uncertainty principle has become a beacon, guiding scientists, philosophers, and artists alike toward a more nuanced understanding of existence. In a sense, its greatest latest lies in its duality. On one hand, it is a precise scientific principle, mathematically rigorous and experimentally verified. On the other, it is a symbol, a cultural metaphor that speaks to the broader human experience of ambiguity, unpredictability, and change. This dual legacy ensures its place not only in the annals of physics, but also in the collective consciousness of humanity. As the world moves into new frontiers of science, exploring quantum biology, artificial intelligence, and the mysteries of dark matter and dark energy, the spirit of the uncertainty principle remains alive. It reminds scientists to remain cautious yet bold, realistic yet imaginative, aware of limits yet open to possibility. It teaches that knowledge is a journey, not a destination, and that even in the presence of uncertainty, progress can be made. Thus, the enduring legacy of uncertainty is one of transformation. It transformed science, philosophy, art, and culture. It transformed how humanity understands knowledge and reality, and it continues to shape the future, ensuring that uncertainty, far from being a weakness, remains one of the most powerful forces driving human thought.